Hello, everyone, and welcome again to the 7th International Electronic Conference on Sensors and Applications. Today for a session focused on students. This conference has been organized by MDPI and their journals Sensors and Chemosensors. And I would like to take this chance to thank our chairs, Dr. Stefano Mariani, Dr. Tom Messervey, Dr. Alberto Bayan, Dr. Stefan Bosé, and Dr. Francisco Falcone. Also to all the people from the conference committee for making this conference possible, and all the participants for joining us today. During this week and until Monday 30, you will be able to assist to several live sessions with excellent speakers and have the opportunity to read and comment all the author submissions presented for the conference. Please look at our webpage during the rest of this month for more updates and register for free for the following live sessions. I would like to remind everyone that this webinar is being recorded and that we also have a YouTube live streaming. The recording will be posted on the conference webpage for everyone to watch it as soon as possible, and I will be sharing the YouTube link through the chat in a few moments. I will now present today's session chair, Stefano Mariani. Dr. Mariani is an associate professor at the Department of Civil and Environmental Engineering of the Polytechnic University of Milan. His main research interests are, among others, the reliability of MEMS that are subject to shocks and drops, the structural health monitoring of composite structure through MEMS sensors, numerical simulations of ductile fracture in metals and of quasi-brittle fracture in heterogeneous and functionality graded materials, or multi-scale solution methods for dynamic delamination in layered composites. Thank you, Stefano, for accepting to participate in this session. The microphone is yours, so everyone enjoy.
Thanks, Anna, for the introduction. And welcome to our today student session. So it's a pleasure to introduce this session, which is sponsored, as Anna said, by Sensors and Chemosensors. So today we will have 9 presentations to be delivered by PhD students, and each of them will have 15 minutes for the presentation, including also some minutes for questions and answers. So I recommend everyone so since we have this quite tight schedule, to be on time with the presentation. So don't steal any further minutes, and I will say let's start immediately with the first presentation, which is going to be delivered by César Prado Soares, from the University of Campinas in Brazil. So Marco, please, stage is yours.
Thank you. Hello, dear friends from the 7th International Electronic Conference on Sensors and Applications. My name is Marco, from the School of Mechanical Engineering of the University of Campinas in São Paulo, Brazil. Today I'll be present to the smartphone-based optical fiber sensors for the assessment of a fed-batch bioreactor. This presentation is a little long because we wanted to give you to those who want to check every detail. So not everything will be detailed here, but you may feel free to ask anything or send us emails or so on. Well, this work is introduced in the context of the Industry 4.0, where the application of novel mathematical and computer-based methods for the optimization and monitoring of systems present socio-economic environmental repercussion on the activities. This new period relies on the development on new technologies. These technologies should be capable of collecting, distribution, and delivering information by themselves. So, in chemical and biochemical industry, such industries may present an increase of the data availability on the portability of the monitoring devices, and this has potential to enhance safety, productivity, energy use, environmental sustainability, and product quality. In the chemical and biochemical assessment, well, this is generally based on high performance liquid chromatographic systems, gas chromatography, as you can see here, and the GC is not here. Coupled techniques like GC, coupled to mass spectrometry, ELISA immunosorbent assay. These methods are, of course, sensitive, reliable, and very precise, but they demand expensive and book instrumentation. They demand highly trained technicians and procedures that take long, very time for the analysis. So on the other hand, the use of compact real-time sensors allows you to monitor, control, and screen the best process conditions with high facility. In this context, the optical fiber sensors presents many advantages to being applied to chemical and biochemical systems. They present reduced masses, low energy costs, resistance to electromagnetic interference. They may perform the remote sensing. They present higher environmental resistance, are inner to both chemical and biological agents. And of course, they present reduced fabrication costs, so they are suitable for the mass fabrication of devices. In this work, our approach was to develop a portable smartphone-based OFS platform that is designed for the monitoring of fed batch fermentation systems. The fed batch was chosen because it's the most way that the alcoholic fermentation industries in Brazil, that are very important industrial sector in our country, operate. And the results were validated through comparison with a handheld reflectometer and with the mathematical models. So, how is the fermentation monitoring and modeling? It's usually focused on the maintenance of the adequate conditions for the microorganisms. It's based on the evaluation of the cell's concentration that is usually expressed as the X. Many of these traditional measurements are based on manual time-consuming procedures. For example, counting with Neubauer chamber, that is a technique where you remove a sample and put it in the microscope to count the cells. Dry mass evaluation, that is a technique where you take the sample, centrifuge it, and dry it to evaluate the mass. And surface plating method, that you put a fluorescent marker, a fluorescent label, and evaluate it in a specific device. So most of the practical industrial cases, in most of them, the measurements and control are actually based on the quantification of specific properties, since these other techniques are not possible. It may be either physical, example, variation of mediums, refractive index, viscosity, or electrical conductivity, or even biochemical, like monitoring the concentration of a specific proteins, carbohydrates, DNA, or RNA. And the properties are posteriorly correlated to the concentration of cells by an appropriate model derived from the fermentation reaction. This is the general fermentation, where cells consume substrates, that's usually sugar, sucrose, and generates products and more cells, what constitutes an autocatalytic process. One very common way to model it is through the Monod model, that it's expressed through these two differential equations, and there are other two, the Ludeking-Perret and this one, that accounts for the product formation and for the consumption of substrates. So in the fed batch reactor, it's a mode where we start with a given volume and initial concentrations of cells, products, and substrate. Products usually 0, and an initial volume V0. So a constant feed flow F supplies it with solution containing fresh substrate and concentration SF. So the differential equations are quite changed to take into account this variation of volume and the dilution and the accresciment, the add of substrate. So our working conditions, we use the specific lineage, the ATCC 7754 of Saccharomyces cerevisiae cells cultivated in East Peptone dextrose, that is a medium already optimized in pH 6.5 to give best conditions. A feed flow containing only sucrose and water in concentration of 30 grams per liter, and the fed with a peristaltic pump. The reactor presents high surface area per liquid column, so it's the surface is kept exposed to the atmospheric air and the magnetic steering, guaranteeing the saturation of the liquid with air. This guarantees the aerobic conditions which are necessary for favoring the cell reproduction over the ethanol production, so the ethanol does not interfere in our measurements. These are the parameters, so everyone can perform the same simulations. And the optical fiber sensor smartphone, it's based on the modulation of the power reflectance caused by difference in the refractive index of the liquid medium. These differences are originated by the consumption of sucrose by the cells, and because the sucrose presents a very high refractive index, very higher than water. So the substrate uptake increase the medium, change the medium's refractive index, and the light transmitted is reflected back in the external medium and reflected back, and the intensity is modulated through Fresnel equation. We use a LED source, the smartphone camera LED, or an external source through a multi-mode silica optical fiber, and a coupler directs back to the camera. So when the light reaches the fiber liquid interface, part of it is transmitted and part is reflected with the intensity modulated through Fresnel law. So the reflected light is redirected to the camera, and we develop an application that processes the data. So here is the Fresnel law with a constant for correction of the power losses. And it's very important to keep all the systems, all the optical fibers in the correct position. So we develop a smartphone case for both keeping the position and to isolate from the environmental light. So this case was developed for Samsung Galaxy 9. The case contains ports for the optical fibers and for the LEDs. It was fabricated through 3D printing using PTFG filaments. Here we have the full project of the case that is already supplied in the supplementary information. And here you can see the full setup where the sensor is simply applied to the liquid. The Android application was designed for processing the intensity signals in Android Studio. The operation chooses the image processing parameters, acquires the optical data by the video capture, and analyzes the optical intensity of the recorded video frames. It has three main fields to fix the duration of the measurements, the interval between measurements, and to define the resolution. It also presents other two modes, where the simple one is to perform the camera adjustments for calibration position. The second one performs the recording in a MPEG-4 extension. So after recording the video, the frames are discretized, and the application reads the camera image, collects the image, and evaluate the image average pixels luminous intention through this equation that's simply explaining how to calculate the average. And then we remove the dark regions. So we have the total number of pixels present on the region of interest. And finally, the processed light intensity data is exported to a text file where the normalized curve obtains the product concentration. So here is a simple photography, and we performed first the correlation between the refractive index and the optical intensity detected. We obtained this direct correlation for concentrations ranging from 0 to 100 grams per liter, and relatively low signal-to rate that increase as the cell concentration rise due to the increase of the scattering by the cells. So we verified that it's indeed possible to evaluate the refractive index, and we performed so the fed batch fermentation. It's very important to notice that in fermentation, related high deviations from the model are usually expected because the models present lots of uncertainties, like temporal evolution of the microorganisms, adaptation to a small difference of substrate, small oscillations of temperature throughout the experiment, and difference from shear stress that stress the cells, etc. So the constant recalculation of the adjusted parameters is a procedure highly suggested. So but in our case, the mathematical predictions represented by this black line here they agree very much with the refractometer signals and also with the R sensor. So our results corroborates the with the refractometer and with the theoretical model. So our refractometer presents high resolution of only 10 to -4 refractive index units, but it's also related to high cost equipment that requires sample collection. In contrast, the smartphone-based sensor is available for online monitoring of the fermentation and predicted a concentration of ethanol of only 3.5 grams per liter, what's 5.36 times lower than the concentration of sucrose. Therefore, the ethanol effect on the refractive index can be indeed neglected. So the design of a portable and low-cost smartphone-based sensor was demonstrated with a sensitivity of 8.5 refractive index units. Due to the limited frequency of data collection, the system is not capable of performing quasi-elastic light scattering analysis like previous works that we performed, but its production are quite inferior. It can be manufactured on site by 3D printed and can be easily integrated to an industrial line. So this last characteristic is of major importance for Industry 4.0. Such integration is not possible for traditional assessment measurements like HPLC, and future works will focus on enhancing the sensitivity and to test it under higher fermentation scales for the evaluation of its performance and analyzing more complex systems. Special fibers and sensors will also be evaluated. And I'd like to thank you all of you to the opportunity to speak in here today, to São Paulo Research Foundation for 2 grants that fund this research, and for our partners, Professor Lucimara Latorre from the School of Chemical Engineering, Professor Cristiano Cordeiro from the Physics Institute of Unicamp, for helping us with the yeast strains and the handheld refractometer and 3D printed, and also to the other the agents from Brazil. Thank you very much.
Okay, thanks. Thanks, Marco, for the nice presentation. I think we have time for 1-2 questions. So anybody in the audience? Alberto?
I have a question.
Yeah. Yes, please.
I would like to know the diameter of the fiber core, and if you have also considered plastic optical fibers instead of glass fibers. Thank you.
The fiber diameter is the standard for the silica. It's about 125 without the extra layers, no? Because we have also a layer of Kevlar and a layer of polyethylene. We are considering, yes, the plastic fibers because it allows us to perform in under more easily ways. For example, we can spin it, we can etc. But it's in the next steps of our research, of course. But by that moment, we had a little problem with the coupler. We didn't have a coupler available that worked well with the plastic fibers, but it will be used because indeed, when using it was something that we noticed that we had to increase the power of the light source because the silica power didn't transmit as well as a plastic fiber would be. So of course, if you use a plastic fiber, you will have a better intensity and so a lower SNR.
Okay, thank you.
Okay, thanks. So I think we are now at 10:20, so we have to move to the next presentation. So Marco, thanks again for the nice presentation. So next presentation will be delivered by Gerardo José Ginovart Panizello from La Salle Universidad Ramon Llull in Spain. So Gerardo, please, floor is yours.
Thank you. I'm just sharing my screen. So well, my